Hi guys, I'm Thomas. So I'm between you and morning tea, so I better make this interesting. Um, okay, and I'm a lecturer in University of Canterbury, and I'm also leading the UC Spatial and Image Learning Group. So in the last 3 years, we've been working in collaboration with Christchurch City Council and the New Zealand Transportation Agency to understand and survey the road surfaces and road signage from some of their data, from some our gathered data as well. And here on the bottom is a photo of our first data collection trip using the UC vehicle, the Lidar, the cameras, and GPS sensors. After we collect the data, the hundreds of gigabytes a trip, we would pre-process them. So sometimes we would stitch the image together. We would also, oh great, there's 3D animation there, where we will also rendering the 3D LiDAR scenes and then just project them onto a 2D image surface so we can easily do machine learning with. We use various different machine learning techniques. The main ones we use are called mask RCNN, which what it does, it just takes a lot of images, takes some software packages, and then uses computation resources to generate a neural network. And what the neural network does is it takes image, it goes through a few different convolution layers, and then gives an output class. So in this case, it's a dog. But not only gives the output class, also gives a bounding box, so where is in the image of that object feature is, and additionally, what's the mask of the object. However, we did encounter a lot of problems. The main problem we encounter is, firstly, 3D learning is difficult, but fortunately, we were able to translate our problem into 2D. But secondly, it's very difficult to identify thin needle-shaped objects. The reason being is orientation in this case is the extra dimension here. And also a lot of the conventional machine learning challenges and data sets identify very similar round objects, square objects. And needle-shaped like objects are very rare, basically. And also we're dealing with very mixed resolutions. And additionally, the algorithm we're using at that time was a state-of-the-art algorithm having trouble with thin objects, as documented by the Microsoft developer blog here, where they have shown needle-shaped objects are very difficult to be correctly identified here. And also we're dealing with poor resolution. So this is, all those examples here are what we call at the limit of the resolution of being visibly seen. Anything worse than that resolution, we're not going to even attempt at labeling them. And we do know our algorithm needs quality information, and those signage are around 30 by 30 pixels, and we'll see, we want to train algorithm to see how good would the algorithm be at identifying those signage at those resolutions. And surprisingly, it's nice to have a good surprise here, the algorithm did quite well. So we did a mixture of resolution methods. First, the algorithm will identify where the signs are, and then use the full resolution of the sign to figure out what type of sign it is. And we were able to get over a 95% accuracy in this. I think in this animation, once in a while, you get a wrong one, actually, but they're quite rare. So, going. It's actually quite difficult to wait until one that's wrong, actually, so that's actually good. So. And then we get to the road surface and road markings. So we took a state highway in the South Island between Oamaru and Waitaki, and we took the LiDAR point clouds and translated into images, and then we did a label on those 2D images. And first we labeled the road surface, but then we also labeled the road length, each individual road length, and also each line markings as well. And because it's difficult to identify kind of very thin object, what we realize is if we kind of just do some transformations, we could reduce this issue of very thin objects. And one thing we identify is in the image, road surface only account for a very small proportion of the image, and the road line markings are even thinner, only about 1 to 2 pixels in this case. So by combining principal component analysis to understand the direction, and then by applying some alpha transformations, we were able to get this image here. And all those transformations are revertible, so that means we can transform it from the original image to this PCA plus alpha and transform images, but after we do the learning, we can transform it backwards again. So it's good to have an invertible transformation here. Oops, it's not working. Oh, just did two. And then we were getting quite good detection for the road surfaces. It went from about 50 or 60% accuracy to over 90% accuracy. And similarly, we're getting good results with road line markings and road lines as well here. So overall, we did some data collection, and we found some useful transformations and methods to improve the accuracy for the road surface and markings. And we actually got a paper accepted in the Visual Computer Journal a few weeks ago, so that's quite good. In the next stage, we're actually building a portable data collection setup that I can plug into my personal vehicle to do data collection, that we do want to get some high resolution images. So on the top of the resolution we were previously getting, and on the bottom of the ones, the type of images we're getting now. So that's kind of all I have. So enjoy your morning tea, guys.